simple overview of chemistry.
Yeah.
We're looking at any two atoms interacting with each other. So, what makes an atom? Neutrons, protons, and electrons. We know their charges, we know their masses. So we can do something about size, we can do something about their charge, so we can look at something about how they interact. If we're going to bring those two atoms near each other, what's the first thing that's going to interact? The electrons. So we're primarily concerned about how the electrons on one atom see the nucleus of another atom, okay, and what happens in that process. All right? So one of the things that we discussed already was like relationships. We got two atoms that don't interact, then start to see each other and can start to interact. And they can move up to dating or getting married. Same idea is happening within chemistry. We're taking any two random atoms and we're seeing how they can potentially interact. Notice that as the interaction increases, what happens between them? They get closer. Okay? So the strength of that interaction has largely to do with the distance between them. Okay? So what we want to do is now apply this out to what we understand for any two atoms. If we bring two atoms near each other, there were a variety of types of interactions we could get. Okay? Those we classified as our bonds. Where our ionic bonds we defined as metal and a nonmetal, so that we could quickly identify something about the characteristics of that bond. After that, we have our covalent and our polar covalent. Technically, you could reference the covalent as nonpolar covalent, but I'm just lazy. Right? What did we decide were our definitions between those two? Nonmetal and nonmetal applies to both, which is a perfectly valid definition. Unfortunately, that doesn't allow us to tell the difference between them. So I want a little bit more than just nonmetal, nonmetal. So polar is charged, but how do you become charged? I mean, ionic is charged as well. So we need something else. Depends on how they share electrons. If they're nonpolar covalent, there's no charge, which means they are neutral and they are evenly sharing their electrons. That's why they're neutral. Okay, so when would we have two atoms sharing electrons evenly? What's that? When they're the same. So if I take the same atom and I bond it to that same type of atom, I'm going to get a zero difference in the electronegativity, and I can define that as my nonpolar covalent bond. Okay. That's a little too narrow, so we broaden that ever so slightly to include one more type of bond class. What is that one extra type of bond? Not oxygen.
Hydrogen.
Hydrogen.
Bonds.
Hydrogen and...
I didn't say this.
Thank you. I heard it over here, but you got a loud so maybe you want to call it. And don't say oxygen. Carbon. The difference in electronegativity between hydrogen and carbon is almost nothing. So we define that bond or that type of bond as a nonpolar covalent bond, which becomes important when classifying how these molecules can interact, which will be the next slide. Polar covalent then is everything else. Okay? Anything that is not the same to same, and anything that is not hydrogen to carbon, and anything that is not involving a metal and a nonmetal. Okay? So as unhappy as you may be with the definition of everything else, it works best for this classification. So you need to know the definition for an ionic bond. You need to know the definition for a nonpolar covalent bond. Polar covalent then fits in every other category. Right? This allows us to give us a quick interpretation of a structure to then do something with. So now the question is, what do we do with it? Yeah.
Is it everything or everything else? I just want to make sure.
Fair enough. Everything else. Okay. Every other atom combination. Okay. These are rules of thumb. They are not perfect. The perfect rule comes off of the exact difference in electronegativity, but nobody wants to memorize the exact electronegativities, so these work. Right? The only reason I mention that is that if you use the textbook to define which type of bond you have, there are some cases where you may end up misclassifying because you aren't using the strictest definition. Okay? When it comes to your exams, rules of thumb work beautifully. Okay? There will not be an exception. Okay? Questions about that? Okay. So now what we want to do is what happens when I take two molecules and bring them close to each other. So there's a lot of stuff on this slide, so let's simplify it down a little bit. I want to look just at the upper right. And what I'm concerned about, that's upper left. Just so you know, in case you missed that. What I'm concerned about now is how the chloride interacts with a different molecule. So it's still an interaction between two atoms. Okay? But now it's a different type of interaction. Why is it a different interaction? What about this now looks like a different interaction? In the previous case, we were looking at a bond. Where's the bond? It's the line shown between the atoms. That is a bond. What is the representation I've now put between our sodium chloride on the left and our sodium chloride on the right? Is that a line? No. Why is it not a line? It's not a bond. Okay? It is something different than a bond. It is a slightly different interaction, and for that reason, we'll call it something else. What we will end up calling it will be a force. Okay? And we'll add some more information to that in a little bit. Okay? But now what I'm concerned about is I've taken my atoms, my two atoms, my sodium and my chloride, and I made a bond. And now I want to look at one of those atoms and how it interacts with another atom on a different molecule. It's still two atoms I'm comparing, but their local environments are now different. Would I expect both of those interactions to be equally valid? Okay, no. Why?
Because the chlorine on one is connected to a metal, and the chlorine on one is connected to a non-metal.
So you're saying the chloride on one would preferentially connect to the metal as opposed to connecting to another nonmetal.
Yeah.
Okay, and that's because why?
The amount of electrons, the one that goes balancing.
So you're getting at the right idea, but you aren't putting down the answer on where it's coming from. Okay, one possibility is we could say, well, chlorine never bonds to nonmetals. That compound is a nonmetal bond, the name. Technically polar covalent, yes. What's the name of that compound? ClO minus. One that you are responsible for being able to name. Chloride is Cl minus by itself, not bound to oxygen, so it's not chloride.
Chlorine monoxide.
Chlor8 doesn't work because that is ClO3. Chlorine monooxygen or monooxide assumes it is just a covalent compound with no charge. This one is charged, so it can't be chlorine monooxide. Now we're starting to get at it. Hypochlorite.
You remember, we were just testing you.
Fair enough. When it comes to nomenclature, you are responsible for that. Okay? That said, I don't think you'll actually be asked that on the test. But you're still responsible for it. The point still stands. Chlorine can bond to a nonmetal. And in fact, I could even have done chlorine bound to chlorine, also known as Cl2, the diatomic chlorine. Okay? So why is that interaction bad? Why is it unstable? What type of bond are red lines? What type of bonds are those? Ionic bonds, because metal and a nonmetal. Why do we call them ionic? And don't tell me because it's a metal and a nonmetal. It's ions. When we look at an ionic bond, we make ions. That's it. What ion do we get from sodium? Sodium ion, I know, fair enough. What charge would it become? What charge do we get when chlorine becomes an ion? Okay, if that's what happens on the left molecule, what happens on our right molecules? Same thing's going to happen, right? Why is the bottom interaction not favored? We bring negative near negative, and like charges repel. Just by understanding something about the bond, I can now start to predict how that bond and the atoms in that bond are going to interact with a second molecule. Okay? That interaction should organize in such a way where we minimize the charge as much as possible. We alternate positive, negative, all the way through. Okay? What happens if we change the bond, though? Same idea. You can even show the red line to represent our bond. Show our purple dashes. Which of these forces would be favored?
This is a trick question.
It is absolutely a trick question. What type of bond do we have? Nonpolar covalent. What charge builds on the carbon?
-4.
The charge is building based on the difference in electronegativity. If it is a nonpolar covalent bond, what is the difference in electronegativity? There is no difference, which means where do the electrons in the bond go? Back to their original atoms, which means there is no charge. I don't know how much I was actually trying. So there's an interesting point. Hydrogen can only bond once. Are we looking at a bond? No, it's not a bond. It's an interaction between those atoms. Okay? So at our first pass, the interaction is equal between both those situations. There is no reason for that carbon-hydrogen bond on the left to interact differently with our carbon-hydrogen bonds on the right. Both interactions are possible. Okay? What happens if we switch to a different type of bond? Let's take a look. Ta-da! Which interaction is favored now? Top or bottom? Why do you say the top?
Positive. Oh, no. No?
Work your way through it. I agree. What type of bond do you have? Is it a metal and a nonmetal? No, so it's not ionic. Is it same to same? No. Is it carbon to hydrogen? What is it then? Polar covalent. By being polar covalent, there is a difference in electronegativity. The electrons spend their time on which atom? Oxygen, the more electronegative atom. So oxygen takes the electrons most of the time and starts to become negative. Okay? It's not formally negative because then it would have to be an ionic bond. It is partially negative. So we have to include that notation. There's our partial charges that we talked about ages ago. And then our hydrogen becomes partially positive. So I heard a question on why did the oxygen become partially negative. Look at the electrons in that bond. One electron comes from oxygen, one electron comes from hydrogen. If oxygen is more electronegative than hydrogen, oxygen is holding both electrons. If oxygen started with one but now gains a second, what happened to its charge? It's becoming negative. It took a second electron on. Started neutral, it's gained electrons, it becomes partially negative. Where did it get that electron from? Hydrogen, which then means if oxygen's becoming negative, hydrogen must be becoming positive. What happens to the other molecules that we have on the right? The same thing. They're still the same type of bond, and oxygen is still more electronegative than hydrogen. So oxygen is still going to take the electrons, and we'll end up generating those partial charges. If we now use that information that we've been doing in all other cases, what do we want our charges to do? Same to same or opposites? Opposites, because what we're trying to do is neutralize that charge. Pair it up so that charge becomes more neutral, not more negative or more positive. Which then means our favorite interaction is the top one, because I can take a positive and pair it to the negative. Okay? That means the bottom interaction is a bad idea. Okay? Because that puts more charge, more positive charge in the same location. Make sense? Okay. So what we've gone through and done has actually nailed down 3 different types of interactions. Okay? In our top 2 cases, the top interaction was our favored one. In our bottom case, both interactions were equally favored. So minimally, we have 2 types of interactions. Okay? To come up with some names for these interactions, we want to think something about how they might be different. So let's think about the top ones versus the bottom one. Which ones do you think are stronger, top or bottom? Okay, and to clarify, let's erase the interactions that don't make any sense. Are we looking at NaCl and OH being stronger than CH or the other way around? The top is stronger because there's an actual attraction. I'm trying to neutralize that charge. Is there an attraction in the bottom one? No. If there's no attractive force, we would predict that to be very, very weak. We would expect a weak interaction in this bottom case. Okay. We might predict it to be so weak that it is irrelevant. Okay. If we have such a mild attraction to somebody else, we don't even consider them as a possible mate, right? Okay. Same thing's happening here. It is so weak we said, I don't care. I'm going to ignore that interaction. Okay. Some smart aleck scientists went back and said, actually, you're wrong. You can't ignore it. It is exceptionally weak, but under the right circumstances, that interaction can cause variations in how we would predict and observe our world. So because of that, him going through and saying, hey, that's an important interaction, you can't ignore it, what do we do to annoy students? Or honor him?
Honor him.
We name the interaction in this kind of compound after the discoverer. That person's name happened to be Roger Rabbit, not quite. Van der Waals. Okay? So we can refer to that interaction as a Van der Waals attraction. I tend to not be a fan of naming things after people because I think it's a bit egotistical. Okay? So I prefer a different name. London dispersion forces.
What?
Give me a sec. The London part, I agree. That's way out in left field. I got no explanation for that. But the dispersion part, that's the important part. Okay? To get that attractive force, we're looking at the electrons around that individual molecule. What are electrons constantly doing? They're cloudy. They're moving. They're dispersing differently. If we assume our atoms do not move, which is a primary tenet of most chemistry, the electrons do move. Okay? I have an electron cloud around this bond. What happens if randomly those electrons all decide to hang out to one side of it? What gets exposed? The hydrogen. In particular, what about the hydrogen? Its nucleus, which has a proton in it which has a positive charge. So if the electrons all happen to disperse randomly to one side of the molecule, what gets exposed? A positive. And if the electrons are all on one side of the molecule, what charge is that side of the molecule? Negative. What have I generated? The partial charges that now explain the forces that van der Waals was looking at. It is how the electron cloud is dispersed through the molecule, hence London dispersion forces. Okay. As you might have already guessed, I'm not a big fan of lots of words. That may not have been a good guess. I talk a lot. I drop it down to LDF. Okay. Probably not something appropriate. So I'll refer to this force as our LDF force, our weakest force. Okay? What happens when we move up to the top? We get a stronger attraction. So both of the ones up top should be stronger than our London dispersion force. Should they be of equal strength?
No.
Why not?
Because one's a partial charge.
One is partially charged, one is permanently charged. Okay? Which one should be stronger?
The permanent charge.
The permanent charge is going to be the stronger attraction. So this will be our strongest force. This one will be our intermediate. And then we have our weakest force at the bottom. The strongest force and the intermediate force, both of those were things that when we at least looked at it superficially, we were like, yes, those are stronger. We should have a legitimate name for those, not naming it after some person that made that first simple observation. Okay? So let's come up with a creative name for these. How do we make the attraction between an ionic compound and an ionic compound? It's really, really creative.
Wait, say it again?
What should we describe as the force between an ionic compound and an ionic compound?
Ionic force.
Very close.
It's an ionic force. That's it. Okay. Could that easily be confused with an ionic bond?
Yeah.
Yes. So this is where it is starting to become more popular to include a different name for the ionic force, because an ionic force is not an ionic bond. They are distinctly different things. Okay? So you may also hear reference to an electrostatic force. Okay? They are both referring to the same thing. We're looking at the attractive force between two unique ionic molecules. Okay? So that was a super creative name. Maybe we're going to come up with an even more creative name for the other one. Okay? Partial force, not a bad idea, but no, not quite. Okay. And in an ionic bond, we've kind of separated those ions away from each other, so we don't really have a bond. The electrons have been transferred from one atom to the other. Okay? In our polar covalent situation, those electrons are actually being evenly shared. So they are tied to each other. Those atoms are tied. Okay? So that molecule on one end of the molecule is positive, and at one end of it, it is negative. Okay? Which is different from the ionic one because we're saying there's not a molecule. They're actually separated. So we have a single unit with two charges of opposite alignments. They're two poles, right? A north pole and a south pole. Okay, so we could call it, the first one, a two-pole. That didn't sound very creative, right? What do we use instead of two? That first molecule has a dipole because it has these partial charges. Well, what does the other molecule have? A dipole. So our force name becomes... That would have been a better force name. Dipole force.
No way.
Like I said, do you really want to change to naming it after somebody? Because that's your other option. At least it comes out of knowing what's happening with the molecule. Okay? And we have the dipole force. So we have three primary forces. Ionic forces, dipole-dipole forces, and London dispersion forces.
Probably 5.
Questions about that? What's that? How do I know which one is which? How did I get the ionic force?
It's a non-monomer bond.
That tracked back to it being an ionic bond. How did I get a dipole-dipole force? That tracks back to it being a polar covalent bond. How do I get a London dispersion force? A nonpolar covalent bond. The forces are tied directly to the type of bond that can potentially generate them. So by looking at your bond structure, you can predict the force. Not only can you predict the force, you now can tie that to the strength of the interaction. And it's that strength of the interaction that we use in chemistry to predict things. Okay? Yes?
Can you go back to how you figured out which one was polar and non-polar covalent?
Okay, so that would be back here. What is our definition for an ionic?
I mean, when you were looking at those specific ones, like, how did you know?
Okay, now I'm a little confused as
Well,
to
like, the
answer
thing
the
you were
question.
doing with, like, the neutral, like, how did you figure out that they were, like, neutral charges, and the other ones were, like, partial charges?
How did we establish the distribution of electrons within an individual molecule? That's what you're asking. What type of bond do we have between sodium and chloride?
Ionic.
As an ionic bond, where do the electrons spend their time? Where do the electrons in an ionic bond spend their time?
Oh, isn't it one?
What is the definition of an ionic bond? The electrons go back to the element that is more electronegative. Okay? There's a large enough difference in electronegativity that the electrons in that bond spend their time solely with the chlorine, because I have a large enough difference in electronegativity that the electrons are actually transferred from the bond to the chloride.
Oh, okay.
Okay? Since the chloride supplied one of those electrons and the sodium supplied the other one, chloride has gained an extra electron through this interaction, which then makes it formally negative. The sodium becomes formally positive. We use that same logic when we look at the bond between OH and the bond between CH. But we have to evaluate again the type of bond. What type of bond do we have between carbon and hydrogen? A covalent bond, or a nonpolar covalent bond, which means they equally share their electrons. So that line represents how many electrons? 2. 1 electron goes to the carbon, started with 1, so it has neither gained nor lost electrons. The other electron goes to the hydrogen. It has neither gained nor lost electrons. So what charges build? Well, nothing. There is no charge differential. What happens when we go through and look at the OH bond? Oxygen is more electronegative than hydrogen, so it will take its original, and half of the time it takes hydrogen. The other half of the time, hydrogen keeps it. Okay. That half split is why we get a negative, because it's got it some of the time, but it only has it some of the time. There's the partial. Okay, does that make sense? So we have to evaluate the bond characteristics to determine our charges. Once we know the charges, we can then predict the force. Does that make a little more sense?
Sure.
Other questions on establishing the charges? Okay, then talk to me after class. Okay. You'll notice that we only covered 3 of those. I didn't cover that last one. It is now suspiciously left available. What's happening in that last case? The bond between oxygen and carbon is a polar covalent bond. I agree, which then means what? Carbon becomes partially positive, our oxygen becomes partially negative. Which interaction is favored, top or bottom? The top, because we get our neutralization of charge. Okay, what type of force would we use to name that force? Let's try that. Name that force. It is a dipole-dipole force. Okay. Next question. Which dipole-dipole force is stronger? Our bottom or our top?
The carbon to oxygen.
So you said the top. Why did you say the top?
Because.
I'll come back to you.
Why did I say the top?
You want me to try the other direction first while you think about it?
Yeah.
Okay.
There's more electrons on the outer.
If there's more electrons on the outer shells, would it start becoming more or less positive? If anything, we have more electrons.
Less positive.
It would become less positive. If it's less positive, what happens to the interaction? Does it start to look more like the CH or more like the ionic? It starts to look more like the CH, which would suggest the opposite of what you suggested. Okay. Where you were starting to go at, because you were looking at the periodic table,
Yeah.
was our electronegativities.
Yeah.
Oxygen versus hydrogen. What is the difference in electronegativity? How far away are they from each other? Really, really far away, which means the difference in electronegativity is really, really big. Where is oxygen versus carbon? Right next to each other. What's the difference in electronegativity? Not as much, which then means the charges generated in our oxygen-carbon bond are going to be relatively small, whereas the charges generated in our oxygen-hydrogen bond will be relatively large. What does that mean about the strength of the interaction in our top case? It's stronger. They're bigger. They're looking more like an ionic bond. Our bottom case is looking more like the nonpolar covalent bond. So that top case is a significantly stronger force than the bottom OC bond. So while they are both dipole-dipole forces, I now want to add to this and be like, well, that OH bond that's going to generate an even stronger force than that OC bond. Okay? I want to describe or name that force because it is significantly stronger. Okay? What do I name that force? The top one. The bottom one is still a dipole-dipole. Well, we needed hydrogen,
No.
and for some stupid reason, we call it hydrogen bonding. It is not a bond. Hydrogen bonding is the interaction between two entirely separate molecules. There is no bond. It is a force between two molecules. Okay? Why do we call it hydrogen bonding? Because to have hydrogen bonding, what do we need?
Hydrogen.
Hydrogen, and it needs to be
Bonded.
bonded to
Another element.
Oxygen.
oxygen,
Close enough.
nitrogen, or fluorine. Why oxygen, nitrogen, and fluorine? What's that? There's a lot more halogens.
They're the first three or next one.
What do you mean the first three?
Well, on the first three before the noble gas.
Okay, why those first three? How did we establish what our bonds were and the strength of those forces?
How far away they were.
From, why were we looking at the distance they were away from each other? Hydrogen, at the extreme left of our periodic table, is the least electronegative nonmetal we've got. Fluorine, oxygen, and nitrogen are the three most electronegative elements on the periodic table. We get the largest differential in electronegativity when I bond those atoms with each other, which is why we define this new force as hydrogen bonding. Okay? That is a requirement in the name of hydrogen bonding. Okay? So let's go through and carefully identify this. To have hydrogen bonding, notice the quotes. Hydrogen must be bound to what?
Oxygen, fluorine, and nitrogen.
Hydrogen needs to have a little phone. Phone. Not my joke. Fluorine, oxygen, and nitrogen. You have to have hydrogen bound to one of those. If you have the physical bond between hydrogen, fluorine, oxygen, and nitrogen, you have the potential for hydrogen bonding, which, notice I'm saying the potential. Okay, what else must be present? A dipole-dipole force. If you do not have the dipole-dipole force, but you have hydrogen bound to fluorine, oxygen, or nitrogen, you do not have hydrogen bonding. Okay? This is why hydrogen bonding, you'll notice, is offset a little bit from the first three, and why we did not talk about it directly. We have three primary forces: ionic or electrostatic, okay, which comes from ionic compounds, okay, or ionic bonds. The London dispersion, or our van der Waals force, came from non-polar covalent bonds. Dipole-dipole came from polar covalent bonds. So we ready to do some examples here? Yes, there's some exciting answers. What type of force is shown within the box?
London dispersion.
Wrong. Wrong. Wrong.
Wait, what kind of what is?
What kind of force?
There's no force.
There is no force shown in that box. To have a force, what do we need?
Oh, gosh dang it.
You're right about the trick question.
Two molecules.
Trick question.
We only have one molecule right now. So if we look at CH interacting with now CH, what type of interaction would I now expect between those two molecules? Now I have van der Waals or LDF forces. What happens if we take our CH? Let's do this. What is the interaction now? This is a tricky one.
I've heard it in movies, that's why I like seeing it.
I'm adding the arrow as clarification here. To have hydrogen bonding, what do we need? Dipole-dipole force. To have a dipole-dipole, what do we need? Polar covalence in two molecules. That's why we call it dipole-dipole. Is there a polar covalent bond in CH?
No.
No. Do we have dipole-dipole?
No.
No. If it's not dipole-dipole, do we have hydrogen bonding?
No.
No. Which then means the force we've got,
Van der Waals.
London dispersion.
London dispersion or van der Waals force. Okay? You have to satisfy all conditions for it to be true. One of the things that I will admit gets tricky is that when we go through and ask questions, we very typically will go through and say something like this. Here's CH3. That's dumb. Let's fix that. What is the strongest force that this molecule could exert if it interacted with another molecule? Okay. Maybe it'll help if we draw out the full Lewis structure. What type of bonds have we shown so far?
London dispersion.
Bonds?
Oh,
Nonpolar covalent, which would suggest London dispersion, which happens to be our weakest force. That's possible. So this molecule does have London dispersion forces. Okay. What happens now? The instant the oxygen comes into the picture, what type of force do I have? Ionic assumes metal and nonmetal. I jump up to the dipole-dipole because I now have a polar covalent bond. The oxygen makes it polar covalent. Okay. This molecule can exert a dipole-dipole force. If I now assume I'm looking at a mixture that is just this molecule, what are the interactions between this molecule and another one just like it? Well, dipole-dipole. If I've got a dipole-dipole force, what do I then need to evaluate?
If there's an
Is there a hydrogen bound to oxygen, nitrogen, or fluorine? Is there?
Yeah.
Yes, which means hydrogen bonding. Okay. We need to be able to look at our structures or our formulas and interpret something about the bond characteristics, because that's nomenclature. Then we have to be able to interpret something about the forces that come out of it. You'll notice up at the top, the types of forces here, I'm labeling them as intermolecular. Inter meaning, it's the other way. It's between two separate molecules. That's intermolecular forces. Sometimes you'll see that abbreviated as IMF, intermolecular. What are bonds?
Two or more atoms.
Bonds are a force but within a molecule. So instead of it being inter, it becomes intramolecular. Okay?
So if you ask that like on a test, would you have to determine both, like dipole, and undergrounding, or just?
Depends on the question asked. If I ask for the strongest intermolecular force possible for this compound, strongest by definition means I want the one that is strongest. The one that is strongest is hydrogen bonding. If I ask what intermolecular forces does this compound contain within it, it contains hydrogen bonding, because that is the strongest one. What else does it have? London dispersion. What else does it have? Dipole-dipole. All three would need to be specified. Okay. Very typically at this level, we're asking for the strongest force. It's not until you move into probably organic where we get to a little bit tricky and say how many of them are there.
Is hydrogen bonding a stronger force than ionic force?
Hydrogen bonding is not a stronger bonding or a stronger force than ionic bonding. Okay. So we now have a way to classify these. The question becomes, what can we do with them? Okay, before we even do that, I personally love this diagram. Once people understand what it means, it works out pretty well. We have, starting at the black box at the lower left of this image, okay, we are starting there with the strongest possible attractive force between molecules. That force is so strong, we call it a bond. It is so strong that we call it a covalent bond. What happens is I weaken the attraction between those two atoms. Well, I start to slide up this wheel until I become a polar covalent bond. As I continue to weaken that bond, or that connection between those atoms, eventually I clear a line where I have arbitrarily established a difference between a bond and a force. Okay. That arbitrary line is up at the top of this curve. What happens is I continue to move around the curve. It continues to become a weaker attraction. So the strength of our attraction moves clockwise from our lower left covalent corner all the way around to our London dispersion force, which is the weakest possible attractive force between our molecules. Okay. That's our summary of all possible forces, okay, or all possible attractions. We have our bond classifications and our force classifications. Once we then separate that into bonds and forces, we can then start to interpret something about it. Let's say I look at a compound and it has a, I don't know, purple bond type. What intermolecular force would I expect from it? A covalent bond generates a purple London dispersion force. It's a direct one-for-one across. What if I have a yellow bond type? What type of force would I expect from that yellow bond type? a yellow force. That yellow force is pretty darn close to where we've arbitrarily dropped the hydrogen bonding label. Okay? It would be an exceptionally strong hydrogen bonding interaction or a weak ionic attraction. Okay? What we're trying to get at with this is that your bonds and forces are intricately tied. Good timing on that. Okay? We want to be able to interpret between them backwards and forwards. Okay? Why do I need to be able to interpret the forces? Well, that's now how the molecule interacts with its environment. Well, I don't know. Is it important to look at how a molecule interacts within its environment? Yeah. It's kind of important how you interact with your peers. That's what our forces are looking at. How can we predict or use that information? Okay? Phase transitions. Okay? Where do we have a phase transition? Give me an example of a phase transition. Solid to a gas. What's going to prevent a solid from moving to a gas? Nothing prevents solid from a gas? Why are we all somewhat solid?
Because if we weren't, we would just fall apart.
We'd all be gases. Do we have phase transitions? What is preventing it from going to a gas? If we drew out a picture of a solid with a bunch of squares,
Temperature?
did I draw a solid or did I draw a gas?
Solid.
I drew a solid versus a gas would look like. What's different between those? The space between them. Okay, what is keeping that space small in the solid?
Forces.
The intermolecular forces. How do we break those forces? With temperature. Temperature is how we measure the energy we use to break those forces. What were we using? We're using heat. Okay? So when we look at a particular material and we notice it is a solid, what can we say about its melting point? Okay, not room temperature. Fair enough. Give me more detail than that. Is it higher than room temperature or lower than room temperature? It has to be higher because if it's a solid, it had better be higher. Otherwise, it would have changed phase already. Okay. How can we use our intermolecular forces to predict this? Let's take a look at some examples here. Phase transitions. Sodium chloride versus water. What type of force do we expect for sodium chloride? Ionic. What type of force do we expect for water? And I guess I should be happy that you're not adding the bonding part to it, but it'd be nice if you added that. If we go back to our beautiful color wheel, where is our ionic force? Up at the top, meaning it is a strong force. Where is water?
Above the middle a little bit.
Hydrogen bonding. Is that stronger or weaker?
Weaker.
It is a weaker force. What does that mean? When we go through to melt salt or water, what are we trying to do? We are breaking the intermolecular forces. Which one requires more heat? Sodium chloride. Which means if we compare sodium chloride to water, we would expect sodium chloride to remain a solid for a lot longer than water. Is that a true observation? Yeah, it works. Okay. By using something about the bonding structure, we can predict these phase transitions. Which one should be higher, which one should be lower. Okay. Let's take a look at a different one. Let's pick... Oh, I'm not being super creative today. Let's do this. CO2 versus water. Okay, and this is where everybody kind of flips out at this. Okay, hopefully you guys will get it right because we've gone through it nice and slowly. What is our force for CO2? I'll work with dipole-dipole. We'll come back to that in a second. What does water have? Hydrogen bonding. Hydrogen bonding is a stronger force than our dipole-dipole. Which one should have the higher melting point? H2O. Is this something that we know to be true in our everyday observation? Yeah. Okay. CO2 is commonly used as an example to explain why covalent bonds are weaker than ionic bonds. Okay. Which, for the record, is wrong, just so you know. Because when we look at sodium chloride, what phase is that? Solid. And when we look at CO2, what phase is that? Gas. So what does that mean? Well, that must mean that sodium chloride has a stronger bond than CO2.
No, it's just a stronger force.
It has a stronger force. Which of those two compounds has the stronger bond? CO2. When we do the phase transition for CO2, what happens to a molecule of CO2? Nothing. Okay. When we're looking at our properties, they come back to our forces. Once we've interpreted the forces, we can then back calculate our bonds. Sodium chloride has a strong intermolecular force, which then means it has a weak bond. That is why it's polar and reactive. CO2 has a weaker intermolecular force, which ends up translating into a stronger bond. It's a neat little transportation between those. Right? As far as how we can use this, we've got our phase transitions. We can use it for vapor pressure, we can use it for viscosity, surface tension, solubility, and ultimately and majorly reactivity. I can use intermolecular forces to predict what type of reaction will occur in organic chemistry just by understanding intermolecular forces and the bonds that make them. Hugely important. Just so you know, we will start with this quiz on Tuesday.